In this video, we'll study the tapped field control and multiple unit control. Tapped field control. It is also called as control by field weakening. When the traction motors are running up to the speed, there is increase in speed possible to the extent of 15 to 30%, which is done by weakening the field strength. The speed for motors is inversely proportional to flux. Therefore, by reducing the field strength, we can increase the speed. To reduce the field strength, we require a diverter, or the field should be tapped. So the advantage of the field control is that it makes the equipment flexible. For example, in city service, low speed with frequent starting and stopping is required. So the equipment can be operated with full field to achieve low speed. When the same vehicle is to be used for suburban service, where higher speeds are required, there is need of gear ratio. So the tapped field, it eliminates the necessity of changing the gear ratio. Hence, one equipment can be used to operate various types of services at a reasonable energy consumption. Next topic is multiple unit control. For city and suburban service, motor coaches are employed, and each motor coach, it has one or two trailer coaches. So the length of the train, it depends on the number of motor coach and trailer coach, which in turn depends on the number of passengers boarding the train. So the number of motor coach, it is different at different time of the day due to the density of traffic. All these motor coaches should be controlled from a single point, which is achieved using the multiple unit control. A unit of train equipment it consists of 2 or 4 motors for each motor coach, which is provided with a series parallel controller, reverser, starting resistance, and collector gear. The controllers and reverser, they are controlled by a master controller, which is available in the cab of any motor coach. The electric cables which are used to join the various units are called coupling cables. Figure shows the multiple unit control. Here we have 3 units to control the 3 motor. So in each unit we have 6 contactors, one for the ground connection, and we have 5 relays, and the starting resistance is from R1 to R4. So the controller in any unit can be operated, and all the motors will start simultaneously. So if controller in unit 1 is operated, that is contactor 2 is closed, then it will energize relay 1 of all the 3 units. When the two extreme left contacts, that is 1 and 2 of the controller in unit 1 closes, the positive collectors of units 1, 2 and 3 will send current through the relay 1 of each unit. The current of relay 1 of unit 3 will pass through the lowermost coupling cable and it will reach unit 2, and in unit 2 it is joined by the current of relay 1 of unit 2. These two currents will then pass through the lowermost coupling cable to unit 1 where current of relay 1 of that unit meets. Then these three currents will travel up to the contactor 2 of the controller, and through the contactor 1 it will flow down to the earthing rail. The relay 1 of each unit therefore will be energized. Each one of the relay will close its own contactor with the result that the positive collector will send current through each motor field, armature, resistance R1 to R4 to the earthing rail. All the motors, they will be started simultaneously with maximum starting resistance in series with each motor. So when contactor 3 of the controller of unit 1 closes, then it will energize relay 2 of all the units, and hence the relay will close its own contactor, which will result in resistance R1 being cut out. Step by step all the resistances can be cut out and all the motors will be in full running position. So all these operations, it is done by one controller, that is the master controller. Next topic is control of single phase motors. So the speed and torque control of single phase AC motors is achieved by applying varying voltage, and no rheostats are used for starting, hence there is no power loss during the starting period. To achieve varying voltage, transformer with tappings on the secondary winding is provided. Figure shows the speed control mechanism for single phase AC motor by applying varying voltage. This is the contactor method of tap changing. So transformer is provided with number of tappings on the secondary, and each control point, it becomes a running point. Also many speeds can be obtained since there are number of tappings. So based on the number of tappings, varying voltage can be applied and different speeds can be obtained. Two successive contactors can be closed on each notch, and each contactor will carry half of the motor current. But precaution should be taken to see to that successive segments of the tapped winding will not be short circuited while changing from one notch to the other. Therefore, preventive coil should be used. This figure shows the contactor method of tap changing for motors employing large currents. Next topic is control of three-phase motors. In polyphase induction motors, the following speed control methods are employed. The first one is rheostatic control. Second one is pole changing. Third is cascade control. Fourth is combination of cascade control and pole changing. First method is rheostatic control. This is the simplest but least efficient method of speed control. Metallic rheostats or liquid rheostats can be used, which will be inserted in the rotor circuit. But liquid rheostats are preferred since they don't have inductance and the resistance is cut off smoothly, giving rise to uniform torque. Also, one economical running speed is achieved because the starting resistance is completely cut off. Also, half of the energy supplied is wasted in the starting resistance. This method is applied to lighter locomotives and motor coaches where single speed is sufficient and the energy consumption is of not much importance. Next method is pole changing. So winding on the stator, it can be arranged with different connections resulting in different number of poles giving rise to different speeds. The choice of the number of poles on pole changing winding is in the ratio 2:1, 1.5:1 and 1.33:1. Also, independent winding, that is one for each number of pole, can be provided on the stator. Next method is cascade control or cascade arrangement. The cascade arrangement is as shown in the figure. This requires two motors which have to be mechanically coupled. The speed of the combination is given by n equal to 120 F1 by P1 plus or minus P2, where F1 is the supply frequency, P1 is the number of poles of first motor, P2 is the number of poles of second motor. The plus sign is used when the torque of the two motors is in the same direction, and minus sign is used when the motors are differentially connected. Next method is combination of cascade control and pole changing. So the two motors will have same number of poles. Therefore, one speed is obtained. But using the pole changing control, the number of poles can be changed and therefore the different speeds or more speeds are obtained.